All right. Hello, everyone. Thanks for joining me for this lecture today. It's on a topic that I'm pretty interested in, and hopefully I'll be able to communicate some of that cool stuff to you. So let's start. Share screen. Okay. So what's the topic of this presentation? Pretty long title. It's on the completeness theorem for propositional modal logic K using the canonical model construction. If all of that is gibberish to you, that's okay. I'm going to be taking some time to go through all the steps of the proof, give a bunch of definitions and so on. So hopefully you'll be able to follow along. And by the end of this lecture, you'll read this title and you'll have a good idea of what it says. Okay. So first of all, what's the intended audience for something like this? Well, this lecture is the final project for a class called Metaphysical Issues in Modal Logic. So a class that involves some use of modal logic. So it's partly intended for my classmates. So what that means is if you have like a basic understanding of logic, if you've done some logic in the past, if you're familiar with what modal logics are, a lot of this should be okay. Similarly, if you don't have the modal logic background, but you understand some stuff from meta logic, which is just the field of logic that studies logical systems and the properties of logical systems, you should be okay. Alternatively, if you're just comfortable with writing proofs, I think you'll also be okay, although some parts are a little more involved than others. But overall, though, I mean, if you don't have any kind of background, it's just going to be a lot harder to follow along, but I am trying to provide as much background as I can in different places. So hopefully this will be able to reach a pretty general audience. Now, note that I'm kind of presenting in different ways the proof of this theorem from James Garson's textbook, Modal Logic for Philosophers. This is the course text that we used for the seminar. And I only mention that because there are some particularities from Garson's system that we'll be adopting. And maybe if you have some familiarity with modal logic, but from a different perspective, it might be slightly different, so it might take some adjusting to. However, most of the I guess idiosyncrasies of Garson's textbook we can largely sidestep because we're just going to be working at such a high level of abstraction. So yeah, that's just some stuff about the intended audience. Okay, so in this section, I'm just going to go really quickly over some background. Yeah, partly because I'm going to assume that a lot of people have some familiarity with this, and because this is like just some boring groundwork stuff. So let's get through this and get to the more interesting bits, right? Okay, so first thing we got to do is just talk about the language that we're working in. Okay, so we're going to be using the language of propositional modal logic. And in this language, so language is just a system of strings, strings of symbols, okay? And then we're going to give rules that tell us when a certain string of symbols has a certain property, namely of being like a well-formed sentence of our language. So that definition just tells us when a string of symbols is like meaningless or if it's like an actual thing that we care about. Okay, so we're just working with symbols right now. Okay, so in our language, we have a list of primitive symbols, arrow, let's call this one bottom. Intuitively, it's going to represent the contradiction, but that's anticipating a little bit, and box. So these are our three main primitive symbols, and by primitive symbols, we just mean that they're not defined in terms of anything else. We'll like state their meanings, but yeah. And we also have a list of propositional variables. So P, Q, R, etc. These are going to stand for sentences, which we'll define in a second. And just parentheses to disambiguate the interpretations of certain sentences. It's not going to really come up that much. Okay, so given those symbols, we're going to define our sentences as follows. Okay, so here we give kind of like what's called an inductive definition. So based on these clauses, we will have defined every sentence of our language. Okay, so our first clause is that bottom and any propositional variable is a sentence. Okay, so whenever we write bottom, that's a well-formed sentence. Okay. If A is a sentence, then box A is a sentence. If A is a sentence and B is a sentence, then A arrow B is a sentence, and no other strings of symbols are sentences. Okay, so A and B here are, of course, just variables over sentences. So let me see if I can draw something. So by the second clause, we would also have like, you know, so for example, if this was A, then clause 2 would tell us that box A is a sentence. And then you can see we can do it again. So if we let this be A, then our clause 2 would also tell us that if we stick another box onto it, we still have another sentence. So adding boxes to sentences, for instance, doesn't affect their, grammaticality, so to speak. Okay. Now, if you're familiar with some basic logic, you might think, well, where are all the other, connectives and stuff that we're used to seeing? Basically, starting out with these primitives, we can define all the rest. Okay, so here's an example. If we wanted to introduce negation into our system, we just define any sentence of the form not A in terms of sentences using symbols that we've already started with. So for example, the negation of A in our language is just going to be abbreviated as A implies bottom. So the idea is anytime you see this string of symbols in our language, it really is an abbreviation for this, and vice versa. Okay, so next let's talk very quickly about proofs. So now that we have a basic understanding, oh man, the annotate stuff doesn't go away, huh? Okay, let me just quickly erase that. Apologies. Zoom stuff. Okay, so proofs are basically properties of sentences in relation to each other. Okay, basically the idea is that from sets of sentences we may prove other sentences. Of course, what does that mean? Basically, a proof is a way to, quote unquote, move from a set of sentences to another set of sentences according to certain rules of the game, so to speak, that we allow ourselves. Okay, and systems of logic basically specify different rules of the game that we're allowed to use to get from certain sentences to other ones. Okay, so these are just called rules of inference. And right here, I'll just give you a quick overview of some of the rules of inference that are appealed to in the system of logic that we're interested in. So for example, double negation. If you start with a string of like this string of symbols, then you can automatically infer this string. Okay, if you start from A, you can infer A. Modus ponens is a familiar one, right? So if you have a sentence A and you also have a sentence A implies B, then you can infer B. Note that from these basic rules of inference, we can derive other rules of inference. So, and these are just the one that we start with, right? Okay, so we can derive, for example, this rule of inference called bottom in, which says if you have A and the negation of A, you can infer bottom. Okay, indirect proof we'll have as well. So if from the assumption that B, one can infer bottom, then we can infer the negation of B, right? Now, one other rule that we will be appealing to, which is arrow falsehood. This just tells us that from a negated conditional claim, we can infer P and infer the negation of Q. And if you recall intro to logic, that is in accordance with the truth tables for material conditional, right? So A arrow B is false only in the case in which A is true and B is false, right? Okay, so based on these rules of inference, these things tell us what to do or what we can do with sentences once we're given them. Okay, now we basically obtain the system that we're interested in called K by taking all of these rules of inferences. So these are the rules of inferences of propositional logic, and we add some extra rules telling us about what we're allowed to do when we have sentences with boxes in front of them or involving boxes. Okay, now I'm not going to go into the details of what box in and box out are. It's not going to be super important for the purposes of our proof that we'll see later. Other things will be relevant, and in those cases, I'll just bring them up. But just know that we obtain K by adding more rules of inference to these rules of inference that I've given. I've omitted some of them just because we're not going to need them. So each of these things that I've introduced, we're going to use at least once in our proof. Okay, now just for a bit of notation. So if from a set of sentences, one infers a sentence A using the rules that constitute system K, so the rules of transformation, let's say, that are provided. If that happens, then we say that there exists a proof of A from S using system K. So what this means is just that, so note this formal symbolism. We're going to write S single turnstile A with a subscript K. This basically means that if you start from a set of sentences S, then using the rules of K, we can prove A, right? So we can infer A. Alternatively, we can read this as S just proves A in K. And in context where it's very clear that we're talking about the system K, we're just going to say that S proves A. Okay, so just remember that whenever you see this symbolism. Okay, now one special rule that deserves mention is called general necessitation. So I bring this up because we're just going to be using this proof exactly, or this rule of inference exactly once. Okay. So what does general necessitation tell us? It's a rule that governs the behavior of box. Okay, so now I'm just gonna highlight something because it's going to be important. So first we're going to need to define something. So if H is a set of sentences of our language, basically box A is going to be the result of prefacing each of the sentences in H with box. So for example, oopsies. So for example, if H is, let's say, and these are just going to be variables for propositional variables. Okay. So B, let's say not B implies C, A implies C. So remember, these are just sentences of H. So if these are our sentences of H, then box H is just going to be the result of adding a box in front of each of these sentences of H. Okay, so why do I bring this up? It turns out that in our proof of completeness, we're going to really be making use of certain kinds of set constructions that are really similar to this. Okay, so this is kind of inconvenient, apologies. I've lost my mouse. it has returned. Okay. So now that we have that out of the way, we can kind of talk about what general necessitation is. So this is a rule of inference that tells us what we can infer once we have a proof, right? So it says that if we have a proof of A from H, so if H proves A in K, then we can infer that box H proves box A. Okay, so if something proves something else, then the boxed version of that something proves the boxed version of that other thing. Okay, and like I said, we're just going to be using that rule exactly once. Just going to give a quick note about K models. So this is moving to our semantics really quickly. So how we understand all these symbols that I'm talking about. Because right now they are just strings of symbols. They don't really have any meanings, right? So what we've done so far is just we've given a string of symbols, and I've given you some rules that allow you to move from certain symbols to other sets of symbols. And we say that, you know, some set of symbols proves another one just when you can transform one of them to the other using the rules I've given you. But when we talk about the semantics of our system, is talking more about like the meaning of the symbols, you know, quote unquote. And this is where K models live. Okay, so briefly, a K model is a triple of objects, W, R, and A, where W is a non-empty set, R is a binary relation on the elements of W, and A is basically an assignment function that maps each sentence of the language at every world W in big W to a truth value, true or false, based on certain semantic constraints we give to A. If that doesn't make a tremendous amount of sense, that's okay, but just note that the set of things in W kind of represent the different points of evaluation, so to speak. So in ordinary propositional logic, an assignment function is just going to map a sentence to a truth value. But here in modal logics, we allow sentences to have different truth values in different points of evaluation. So think of them as like worlds, right? So a sentence might be true in one world or and true in another world and like false in a third world. And we represent that in our semantics by saying that like A assigns that sentence the truth value true in world 1, A assigns that same sentence like false in world 2, and so on. And the purpose of R is to tell us when worlds stand in a certain relation to each other. That's going to be important because that figures into the truth conditions, let's say, of boxed sentences. And again, I'll get to all that stuff later, so don't worry too much. I have to erase this before I move on. Just sorry about that. It's not the greatest at Zoom at the moment. Okay, so last slide of this section. What is this lecture aiming at? Again, so we're trying to prove the completeness theorem for K that I've described earlier. So basically, once we specify semantics, a lot of things are just going to come out as true or false, okay? And what completeness tells us is that our proof system, or all the rules of inference that we've given, are like good enough to prove all the truths that are true based on our semantics. Again, I'll go over the details of this in the next like immediate section. Okay, and I'll also give a note about the particular form of proof of this theorem that we're given. So we're going to be using the canonical model construction to prove this theorem. That should tell you that there are other ways to prove this theorem. And so, you know, why are we looking at this one? So the reason why, or one reason why this method of proof is really interesting is that it's quite powerful. And by powerful, I mean that once you prove this completeness theorem for K, basically the way in which we do that using the canonical model construction will allow us to prove similar results for different logical systems based on K. So if you remember from class, we looked at a system called M, So M is essentially the result of adding an axiom to K. So adding another sentence to K, or in this case, it's like a schema, but whatever, right? So if we add this axiom, box A, arrow A, then we actually get a new logical system in K. And the idea is that once we prove completeness for K, it's going to be very easy to prove completeness for this new system M. Okay. That all this material is in like a bonus lecture I've included at the end. So if you stick around, if you're brave enough to stick around, you'll see the fruits of your labor. Okay. And similar results go for the other systems that we looked at, right? So D is the result of adding to K this axiom, box A, arrow, diamond A. B, we have something similar, 4, 5. Basically, a lot of the systems of modal logic that you're familiar with, like S4 and S5, we're going to be able to obtain completeness theorems for those logical systems in a very elegant and systematic way. So if those things are important to you, might be worth sticking around for the bonus lecture. Yeah, a lot of insights to be gained from general proof methods. And okay, so that is the conclusion of this introductory section. Hopefully you stick around for the next section and I haven't lost too many people. Okay, thank you. Hello, everyone. Welcome back. So hopefully you've made it past the intro section, and real quick, we're just going to go over part 1. So we're getting closer to what the theorem is. And in this section, I just want to give an overview of what the theorem is and tell you something about how exactly we're going to prove it. Okay, because even in like setting up the thing that we want to prove, there's going to be certain steps that make our lives a lot easier. And yeah, hopefully once you have this kind of general information, you'll be able to follow along with the proof a bit easier. And I'm giving this because it's not a super easy proof. It's pretty involved in some parts. So just a warning. Okay, so what is the theorem? Okay, before we state it, let's quickly give some definitions. So say that an argument written H/C is a list of sentences. Sorry, I'm just moving something on my screen that you can't see. Yeah, is a list of sentences H called the hypotheses, followed by a sentence C called the conclusion. Okay, so basically this is like a very bare bones understanding of what an argument is, right? So an argument is just a list. It's just a list of sentences. We call the last thing on that list. So if we have like A1, A2, blah, 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 AN, like this is an argument, okay? Except we're going to treat all of these as the hypotheses, and we treat this as the conclusion. Okay, the reason why I give that is just there's going to be some properties of these lists of sentences that we'll look at in a moment. Turns out that one of them we can talk about is semantic consequence, right? So we say that C is a semantic consequence of H in K models. So we're just going to drop mention of K because it's clear that we're talking about K. We write semantic consequence using the double turnstile. So no, this is not the same as the other one we looked at. This has 2 bars, horizontal bars, right? So C is a semantic consequence of H just when, or if and only if, for all K models WRA and all the W's in big W. If A assigns the hypotheses to true, then A assigns the conclusion to true. And note that W is entirely arbitrary, right? So what this tells us is that if C is a semantic consequence of H, then that just basically means that in every world, in every K model, if the hypotheses are true, then the conclusion is true. Okay, that's just some definition. So here's a completeness theorem, right? So what does it tell us? It tells us, and I'll say more about K validity in a second. I haven't defined it. I recognize that. Let me just highlight that. Okay. So more on this in a moment. Okay. So if the argument h/c is k valid, then h proves c in our proof system k. Okay, so note that this is like k models is like lives in our, that's like our semantic side. This proof lives in our syntax side, and that's partly why the completeness theorem is so interesting. It states this connection between the interpretation of certain symbols with the rules that we allow ourselves to use that govern when we're allowed to transform certain sets of symbols into other ones. Okay, or obtain or whatever. Transform works fine as well. So turns out that this notion of k-validity that I haven't talked about yet corresponds to semantic consequence. And so this is just the alternative statement of the completeness theorem that we're going to be working with. So it says that if C is a semantic consequence of H, given our semantics K, then H proves C in K. Okay. Hopefully, I'll say more in a second. Okay, next slide. So that's the completeness theorem. We're going to prove this by proving it in a different form. Okay, so if you remember from basic meta logic or just logic, so here is typically like one rule of inference. So from A arrow B, infer the contrapositive, which is the negation of B implied, or negation of B arrow negation of A. And basically, I'm not going to talk about like meta languages or anything, but anyway, we have this. It's not in K, it's in like the system that we're using to like prove things about K in, but that's like an added technicality thing. Basically, the important thing to notice is that this, I'm not sure if you can see me moving my mouse, but this is equivalent to this. So if we prove this thing, then we automatically prove this thing as well, right? So yeah, I note that because we're not going to be proving this. Instead, we're going to be proving the contrapositive of the completeness theorem, which is basically this thing. And this says, well, the way you read it is if H doesn't prove C in K, then C is not a semantic consequence of H. Hopefully I said that right. I'm not going to do this again, but yeah. It basically says that if there's no proof of C from H using K, then there exists a K model that demonstrates that the argument H/C is not K valid, i.e. that C is not a semantic consequence of H and K models. Okay, so now I'm just going to unpack really quickly what it means for, let's say, a K model to demonstrate that the argument H/C is not K valid. Okay, so here's where I'm just going to define K validity, right? So an argument H/C is K valid if it has no K counterexample. Okay, that's meaningless unless I tell you what K counterexample is. Good thing I do, which is right here. Okay, so a K counterexample. So an argument H/C has a K counterexample if and only if the list H, not C is K satisfiable. So think of this as just the set of all the sentences in H plus the negation of C. Okay, again, K satisfiability defined as follows. A list of sentences U, so including this, is K satisfiable if and only if there exists a K model WRA for a language containing sentences of U and a world in that model, in that set of worlds W, where A sub U equals true. Okay, so basically a list is satisfiable if there exists some world in some model on which that list of sentences is true, is all true. Like every sentence in that list is true. That's what it means for a list of sentences to be satisfiable. We add the K satisfiability when we specify that we're talking about K models. Again, I'll note some more details later on. So basically, what the completeness theorem tells us is that if there's no proof of C from H using proof system K, then there exists, what the heck? My mouse just like disappears. then there exists a model M in which the list H, comma, the negation of C is K satisfiable. Okay, that is, there is a K model M and a world W in the set of worlds W of M such that A maps H to true in that world W, and A maps the negation of C to true in that same world when there's no proof of C from H. So what this means essentially is if you can't prove, okay, if you can't prove C, then I can give you some world in some model according to which H is true and the negation of C is also true. So I can demonstrate, so once you don't have a proof, that means that you have a counterexample to that argument. Okay, so hopefully that makes enough sense, and hopefully it'll become clearer as we go on as well. Okay, so that's just what the completeness theorem kind of tells us. It says, like, when you don't have a proof, we're going to have a counterexample in our semantics that demonstrates that, like, the thing you want to prove is actually like not a theorem, so to speak. Okay. Now, the way in which we prove completeness really turns upon this stuff involving the models, right? So the way that we prove, recall the contrapositive, is we're going to assume the antecedent, so we're going to prove it directly. We assume the antecedent, and then we show that on the basis of the antecedent, we can prove this, that C is not a semantic consequence of H. And note that in order to prove this, we have to show that there exists a model that satisfies the list H and the negation of C, right? So that's what's going to constitute a counterexample, okay, counterexample, recall. Okay, so this model that we're going to show or construct is called the canonical model. Okay, so basically we assume the antecedent, and then on the basis of this, we construct a model with the properties that we want. Namely, we construct a counterexample. Okay, and we give it a special name called the canonical model because the way in which we construct this model is pretty abstract and uniform, and it's going to work in a very general way. So that's how we get a proof of completeness. Okay, so the million-dollar question is, what is this model, and how can we construct it in a way that guarantees the kind of generality that we want to prove the completeness theorem, right? Okay, so that's largely going to be the focus of this lecture, actually, what this model looks like, because we see that it has to satisfy two things, right? So one thing is that it has to be a counterexample of the sort that we're interested in, and it also has to be a K model, right? Right, because K validity is specified in terms of K counterexamples, which is specified in terms of K satisfiability, which is specified in terms of K model. So it's all like adding K to these sorts of things. So the model that we construct also has to satisfy additional properties, or conditions, namely the conditions that make a model a K model. Okay, so that's just an overview of what we're going to do. Okay, so as a quick recap, okay, we're going to prove completeness by proving it's contrapositive, right? So if there's no proof of C from H in K, then C is not a semantic consequence of H. And we're going to prove this statement directly. So if we assume this, we can construct a K model on which the list H and the negation of C is K satisfiable. Okay, so in many ways, this is like the last intro part of this lecture. So from here on out, it's going to get significantly harder. That's just a warning. But conversely, or on the flip side, it's going to get a lot more exciting. That's just me though. Maybe you think so too. Okay, anyway, that completes this part of the lecture. So hopefully you stick around for the next part as well. Cool. So I'll cut the recording. All right, everybody, welcome back. So this is going to be part 2 of our lecture. there's, I believe, 2 more parts, one of which is the bonus part, so just one more. But this section is devoted to defining what this canonical model is supposed to look like. Okay, so recall our goal is to prove the contrapositive of the completeness theorem, right? So we need to prove that on the assumption that there's no proof of C from H in K, that there exists a K model on which the set H and the negation of C is K satisfiable. So the model we're after must be a K model and must be such that in it, we have this as satisfiable, okay? So as a pedagogical move, I'm going to split this task into 2 sections, okay? So this is slightly different from the way Garson presents it. In the first part, I'm going to construct the canonical model and then show that on the canonical model, we have H and the negation of C being satisfiable when H doesn't prove C in K. So that's just proving that on this constructed model M, we have this part satisfiable. Okay, and then we have to, like the second part is really important because we have to show that the model we construct is in fact a K model, right? Because K satisfiability requires there to be a K model. Okay, so I've chosen to split the task up into these 2 sections because both parts are actually quite difficult, and so it's always easier to communicate this sort of thing when you break it into parts. And I think that the proof that our canonical model M is a K model is just going to seem a lot more motivated once we already know that it satisfies the right sentences, so to speak. And once we know that, we can see very clearly that, well, now we just have to show it's a K model and then we're done. So that's our tasks. So in this section, we're going to be concerned with constructing the canonical model M. However, before we do that, we have to prove, or at least demonstrate how to prove a quite famous lemma. Yeah, so it's kind of exciting, but it's going to be quite difficult, so be warned. Okay, so in this section, we're going to prove, or again, give a proof sketch of the Lindenbaum Lemma for the case of propositional logic. And so just a disclaimer to, not a disclaimer, but like a heads up for what we're doing, right? We know that ultimately the model we want to construct is going to be a triple of this form, because that's what K models look like. And so the challenging part for us will be selecting the appropriate W, R, and A such that our model is going to satisfy the right properties, namely all those properties that K models satisfy alongside the property of satisfying this list of sentences. Okay, so again, let's move on real quick. These are just some notational things, right? I've kind of been doing this already, but when M is a set of sentences, we write M comma A to indicate the result of adding A to the set M. So note this even works if M is infinitely long, okay? You just add another one, and M comma A is going to differ from M in the sense that M comma A has A as an element, whereas M does not, okay? Again, same notation for proofs. Although note here, we're explicitly discussing finite proofs, okay? And basically the idea behind that is that when you have a proof of a certain sentence on the assumption of certain hypotheses, the number of steps it takes to prove that sentence is finitely long, okay? So you can't have an infinitely long proof. There are systems of logic on which that assumption is relaxed, but we are not looking at those systems. Okay, so the importance of finite proofs is this. It allows us to make certain kinds of inferences. This is one that appears multiple times in our proof. So if M proves C, regardless of what system we're in, we can infer that there is some finite list H of sentences of M such that H proves C, right? So even if M is infinite. Okay, so the idea is if an infinitely large set of sentences proves some other sentence, then there's some finite list of sentences in that infinitely large set of sentences that does the same job. Okay, that's just to make that explicit. Okay, now let's move to some definitions. So let S just be a proof system. So for example, K is an example, but doesn't have to be. Right? So this is kind of like general definitions. Okay, so say that set M prime is an extension of M if and only if every element of M is an element of M prime. That's fairly straightforward. A set of sentences M is consistent in S, that is consistent relative to the rules of S, if and only if M doesn't prove bottom in S. Okay, so what this says is that a set of sentences is consistent relative to a system of rules just when you can't prove a contradiction from that set of sentences using those rules. Okay, a set M is maximal if and only if for every sentence of our language A, we have A or its negation as an element of M. Okay, so just imagine, and we'll see, this will be concrete in a second, you had a list of every sentence of our language, right? And so on. For each of these sentences, you either have S1 or its negation. So one of these is going to be in M when M is maximal consistent, right? It's either this one or this one for every single sentence of our language. Okay. Next, we define this very important property called maximal consistent. And it's exactly what it sounds like. All we've done is taken these two properties and smushed it into a single property, okay? And so M is maximal consistent if and only if it's maximal and it's consistent, again, in S. Okay, and just as a quick note, maximal consistent is not the same as consistent and not the same as just maximal, right? So you can have consistency without maximality. So just imagine a set of sentences with like the single sentence P, okay? By construction, it's not maximal because it just has one thing in it. And it's not, I'm not going to prove that you can't prove a contradiction from it, but just take my word for it. Like for some arbitrary P, you're not going to be able to prove a contradiction. It's just like not enough stuff. But then we'll see later, you have to kind of assume soundness for this. And I'll explain later what that is. But you can also have maximality without consistency. So for example, just let O contain every sentence of our language. Okay, by construction, O is maximal. It's also inconsistent since it proves A and it proves not A, which from bottom in means that O proves bottom. And by definition of consistency, it's inconsistent. Okay, and just to be real quick, O proves A, O proves the negation of A. But the negation of A by definition, if you recall, is just A arrow bottom. Okay. And then from these two, you can just use modus ponens because it's still within the same proof, or prove both. And then you get bottom. Contradiction in is just the derived form of this step. So hopefully that's clear. Okay, and finally, instead of saying maximal consistent every time, it's just too many words and life's too short for that. We're going to just say MC. Okay, so whenever you see MC, just think maximal consistent. Okay, so on to Lindenbaum Lemma. I'm just going to call it the Lindenbaum Lemma. What does it say? It says that every consistent set has an MC extension. So for example, suppose we have some arbitrary set of sentences N, and I know it's consistent, right? So let's say it doesn't prove bottom. Then that means there's, by Lindenbaum Lemma, it tells us that there exists some other set n prime such that n is MC, and that every element in n is an element of n prime. That's what it means for n prime to be an extension of m. And MC, well, we just went over that, it's maximal consistent. Okay, so I'm just going to give a proof sketch of this lemma. It's actually one of the most important lemmas we'll be needing in our proof. So yeah, I should say something about it, right? And it's actually, if you've taken courses in meta logic, this comes up a lot. And it's pretty cool. So the basic idea behind the proof is that we're going to demonstrate a method of kind of constructing new sets of sentences from an initial set of sentences. So the idea is that we start with a set M, and then we have like a list of all the sentences of our language, and then we keep on adding sentences to M. Okay, and for each extra addition that we make, we want to ensure that the result is consistent. The idea is that eventually like M becomes large enough to the point where it's maximal and consistent. And clearly the result is going to be an extension of M, because all we've been doing is adding stuff to M, which means that every element of M is going to be an element of the result. So that's the basic idea. I'll go into slightly more detail now. Okay. So like I said, the idea is that we start with a consistent set M, and then on that basis, prove that there exists a MC set M that is an extension of our set M. Okay. So there's basically two stages of this proof. Okay. So in the first stage, we demonstrate a method for adding sentences to M so that the result never yields an inconsistent set. Right. So the idea is, imagine we start with M and add a sentence to M to yield M prime. Again, M prime is clearly an extension of M. And then we have to describe how this procedure of adding stuff to M ensures that M prime is consistent, and that repeated applications of this procedure will preserve consistency. Okay. And in the second step, we're going to define a new set M that is to be the MC extension of M using the results of this procedure just described. Okay, so I'm going to pause for a second and let you read that while I just turn my page. Okay, so here is the rough idea. Okay, so suppose we have an ordered list of all the sentences of our language, and this is going to be infinite, right? So this is going to be A1, A2, up to AJ, blah, blah, blah. And note that A sub 1 refers to the first sentence in this list, and A sub I refers to the ith sentence of this list, and you get the gist. So now the idea is that we're going to define an infinite series of sets, M sub 1, M sub 2, blah, 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 such that each M sub I is consistent, with the idea being that M sub 2 is defined from M sub 1, M sub 3 is defined from M sub 2, and so on. So the idea is every subsequent M is going to be defined using the materials from the one previous. Okay, so here's just a sketch, right? So we're going to let M1, M sub 1, so the first in our infinite series of M's, be this set M that we've assumed, right? We're starting with a consistent M. And now consider A sub 1 from our infinite list of sentences. Okay, so now, in order to get to M sub 2, right, because we want to define M sub 2 in terms of the M sub 1, okay, we're faced with a choice, okay, and we have A sub 1. Okay, now, either we add A sub 1 to M sub 1, or we add its negation. And the way in which we do this is as follows, okay, so suppose by adding A sub 1 to M, right? So the result is we're going to write M sub 1, A sub 1. So this is just the result of adding A sub 1 to M sub 1. If we're able to prove bottom, okay, then we add the negation of a sub 1 to m sub 1, and then we define m sub 2 as m sub 1 and the negation of a sub 1. Okay, so if m sub 1, a sub 1 proves bottom, then m sub 2 equals m sub 1, comma, the negation of a sub 1. Okay, but if I can't prove a contradiction after adding a sub 1, then m sub 2 is going to be equal to m sub 1 and a sub 1. Okay, so it's, you kind of have a choice, not really a choice, what kind of a choice, to define the next one, right? So again, the idea is from this infinite list of sentences and beginning with m sub 1, right? We know m sub 1 is consistent because it is the set M, and we assume that M is consistent. We're faced with a question, right? What happens if we add a sub 1 to m sub 1? Okay, if the result allows us to prove a contradiction, then define the next set to be m sub 1 with the negation of a. Okay, so that's what m sub 2 is going to be. But if you add a sub 1 to m sub 1 and you can't prove a contradiction and you can't prove bottom, then let m sub 2 be m sub 1 with a sub 1. Okay, so a little bit more detail. Again, more schematically, right? So we're assuming that m sub 1 is consistent, and we have our list here, and this is what we want. M sub 2 is going to be m sub 1, comma, a sub 1, if the result of adding a sub 1 to m sub 1 doesn't prove bottom, again, mentioned, or it's going to be m sub 1 with the negation of a sub 1 if m sub 1, comma, a sub 1 proves bottom. Okay, so the choice kind of pivots around whether or not we can prove bottom or not, right? So if yes, then add the negated version. If no, then just add. This is atrocious, I know, but that's what we got. Okay, m sub 3 is going to be defined in a similar way, but instead for the behavior of m sub 2, right? And considering the next sentence on our list. Okay, so for m sub 3, we look at a sub 2, okay, and then we consider, if we add a sub 2 to m sub 2, right, these are the same, are we able to prove bottom or are we not? Okay, if we can prove bottom, then we add the negation of a sub 2 to m sub 2, and then we define m sub 3 as the combination of m sub 2 and the negation of a sub 2. Okay, now if m sub 2 and a sub 2 don't prove bottom, then we'd let m sub 3 just be m sub 2 with a sub 2. Okay, you can see a general pattern here, right? M sub I plus 1 is going to be m sub I with a sub I if m sub I and a sub I don't prove bottom. Or it's going to be m sub I with the negation of a sub I1, or a sub I, sorry, if m sub I and a sub I prove bottom. So that's just the general idea, right? So the result is that we're going to have like this infinite series of sets, each of which is like defined from like the previous sets, based on whether or not the addition of the next sentence of our language to the previous set allows us to prove bottom or not. Okay. So this is like the picture that we have, right? So for m sub 1, remember, this is just m. Now m sub 2 is going to differ from m sub 1 in that either we add a sub 1 to it, or sorry, I'll correct that in a second, right? So in order to get from m sub 1 to m sub 2, we either add a sub 1 to m sub 1, or we add the negation of a sub 1 to m sub 1, right? Based on whether or not we can prove bottom, okay? Similarly, for the next one, right? This is going to be either a sub 2 or the negation of a sub 2, okay? Similarly, okay, a sub 3 or the negation of a sub 3, okay, and then you can just imagine, okay, this is going to be either a sub I or the negation of a sub I. Okay, so here, right, m sub 2 is going to be, we're going to write it like this, m sub 1 or a sub 1 or m sub 1 with the negation of a sub 1. Okay, and the important thing is that in each case, this differs from m1 by this sentence, right? If we're adding this new sentence to m sub 1 to get m sub 2, then m sub 2 is going to differ from m sub 1 by that one sentence. Okay, so this is like the general picture that emerges. Imagine we just do this infinitely, right? Eventually we cover, or like, we cover every sentence of our language, right? And so the next step is to define m as kind of the combination of all of these sentences that we're adding to each subsequent m sub I, okay, and m, right? So it's basically m plus, based on whichever one you add. Let's say you add this, okay, and then you add this, you add this, let's say, continue, and then we add this. Okay, so for each of these a's that actually get added to the previous m to arrive at this m, we're going to take all of those and smush it together into this single set m. And m also includes all the original elements of our set m that we started with. Now, you can see that, it's very easy to see that little m is an extension of big M, right? Just because by construction, it includes all the elements of big M. It's kind of clear that it's going to be maximal, just insofar as, for our infinitely long series of sentences, we also have like a corresponding infinitely long series of like m's. And for each subsequent m, we're adding like new elements of this sentence. That little m is going to include all of these sentences, right? So eventually, I'm skipping a lot of steps just to give you this sketch, right? But the idea is that m is going to be maximal. Little m is going to be maximal. Okay, but remember, we have to show that it's MC, right? So if we know it's maximal, the only thing left to do is to show that it's consistent. And here, there's just going to be 2 steps, and I'm not going to go over them. Well, I'll give you a sketch, right? Oh, I guess I'm not going to go over the sketch. Just real quick, it involves proving that each of these is consistent. And on the basis of that, it kind of falls out that this is going to be consistent as well. Yeah, sorry for that hiccup. Okay, cool. So this is just a quick recap of the section. I know that it's a lot. It's not a super easy proof, but it's not terrible once you're a bit comfortable with these things. But if that's the first time you saw this, understandably it's very difficult. But what's important is just that we know that this holds. Okay, we're going to be appealing to this at multiple points in our proofs. And so just understanding that this holds and knowing like what it means is the important bit, okay? And yeah, just consult chapter 9 of Garson's text for more details of the proof as I presented it. And again, if none of that makes sense, that's okay. But yeah, that's the conclusion of this section. Thanks for watching. All right, hello everyone. So in this next section, we're going to define what the canonical model is, and then we're going to show that it satisfies the right sentences that we need. Yeah, so let's get right to it. We'll see that we're going to be using the Lindenbaum Lemma already. Okay, so this is just one of the moments in which we use it. So all that stuff that you might have suffered through, maybe you'll see that it was worth it. Hooray. Okay, so this is how we define the canonical model. Okay, so recall our system K is just a bunch of rules, right? So some rules of propositional logic, plus these added ones from Garson's text that I haven't given to you yet because it's not really relevant and still not going to become relevant for a while. But just know that K is like a system of rules, right? And that's how we defined proof, right? So H proves C in K if from H we use all these rules and we can conclude C somewhere. Okay, now we define the canonical model M for K as follows, right? We know M is going to be a triple because that's what K models are. Now we have choices for the individual W, R, and A. Okay, so we're going to let W be the set of MC sets for K. Recall that consistency was kind of relative to a proof system, right? So we know that each of these elements, so these are just elements of W, right? I'm just drawing them out. Each of these are going to be maximal consistent sets relative to K. Now, the definition of R, we say that the elements of W are related, right? If and only if for all sentences B, if the first proves box B, then the second proves B. Okay. Note that this does not imply this. Okay. We'll see that in some systems. In the bonus lecture, some systems do allow for this inference to always be a good one, but not in K. So that's the definition of R. Now we define A as follows. Okay, and you'll notice we're actually doing we're smuggling a lot of proof stuff into our semantics, which is just interesting. Right, so here's how we define our kind of assignment function in our model, right? So our function A is going to map the sentence A to true relative to world W or in world W if and only if that world W proves A in K. Okay, so if the world proves something, then our assignment function takes that something in W, in that world, and sends it to true. Okay, so that's the definition of the canonical model. I think a lot of these notions might become more clear when you see it like actually used. So if it's unclear, you'll hopefully get a better feel for it. I'm going to include like the definitions and stuff on the side of the screen too, just so if you ever need to look back, it's there. Okay, so now what we need to do is that based on our canonical model, right, we're going to assume that H doesn't prove C, and then we show that on that basis, M satisfies H with the negation of C. Namely that there's some world W in M, in the set of worlds W in M, such that A with that world maps H to true and not C to true. You'll see. And I'm just going to omit the subscript because it's clear we're talking about K. No, I guess I didn't. Well, sometimes. You know what I'm talking about. Okay. So again, this is our theorem. The way we prove it is directly. Okay. So we're going to assume the antecedent, and what we want to do now is prove the consequent. Okay. Now, the first step that we're going to do after making this assumption is inferring that the result of adding the negation of C to the set H doesn't prove bottom. Okay. And this is fairly straightforward by indirect proof, but here's just an illustration, right? So assume the opposite, assume what happens if it does prove bottom. We're going to show that we can derive a contradiction. Okay. Now this, within our natural deduction system, looks a lot like this, right? It's just an abbreviation of this. Okay, now, but indirect proof tells us, right, that whenever we have something of this form, right, we infer the negation of this. So we're going to get not C, right? So that means that H is going to prove not C. But then by double negation, H is going to prove C. Okay, which is a contradiction because we've already assumed that H doesn't prove C. So therefore, we can't have this, okay, which means the negation of C with H doesn't prove bottom, right? Because this, if we assume the opposite, we get a contradiction. Okay, so that's step one. Step two, we infer that H with the negation of C is consistent. That's just the definition of consistent sets. If you need a refresher, it's in a previous part or lecture part. Okay, now notice that H with the negation of C is a consistent set of sentences. We just proved a really nice lemma that tells us something about consistent sets of sentences, namely that for each consistent set of sentences, there exists an MC extension of it, right? So now we know that there exists some set W that is MC, and such that every element of this set is in W. Okay, that's just comes from the extension part. Okay. Now, step 4, right? Since W is an extension of H and the negation of C, it follows that for every sentence B in this set, okay, W proves it. Okay. It's straightforward just by reiteration, right? So if you begin with A, you can prove A. Okay, straightforward. You can just seems uninteresting, but you know that's a rule. Okay, so this is just by definition of extension, right? Because we see that W is just going to include everything in H and C, and so obviously everything in here, if it's in here, we just apply this rule to get it, right? So that's what this is telling us. Okay. It even includes H and the negation of C, right? W includes H, so it's just a one-step proof to prove H. I'm technically omitting some details just because H is like could be a set of sentences, a bunch of sentences, in which case you might have a bunch of different steps, but each step is going to look the same, right? It's just reiteration. You know, in order to, because W itself is just a set of sentences, including all of those in H. So you just take each of them and like paste them into your proof, and it proves H. Okay. Similarly for the negation of C, so W also proves the negation of C. So we have these two things. This just follows from the definition of extension, which we got from Lindenbaum Lemma. Okay. Now here's the important part. Consider our canonical model M, right? We know that W is going to be an element of big W of M, right? So that just follows from the definition of W. Okay. W is the set of MC sets for K, right? W is an MC set of K. Okay, so W is in W. Now, recall our definition of our assignment function in the canonical model, right? A sub W, so A maps the sentence A to true in the world W if and only if that world proves A. Okay, so we have that W proves H, right? So we have this right side satisfied. Now we know that A sub W of H is going to be mapped to true because W proves it's true, or W proves it. Okay. Similarly, we have A mapping the negation of C to true in W because W proves the negation of C. Okay. Both of these things just follow from this, right? These two things are in some sense like the right-hand side being satisfied, and then you go from right to left. Okay. And in fact, we're done. right? So we've assumed, right? We started by assuming the antecedent that there's no proof of C from H in K. It follows that we've produced a model and a world in that model according to which H is mapped to true and the negation of C is mapped to true. And by definition of satisfiability, we have that M satisfies H and the negation of C. That's okay. It's kind of awkward formulating that last part just because I only define like K satisfiability. And if you recall, like that's just because of that pedagogical move I wanted to make earlier, right? Breaking up our tasks. Right, and I've noted it here. We have a loose thread, right? We don't know if M is a K model yet, but the point of this section is to show that our canonical model M does satisfy the right sentences, right? It is a counterexample. We just don't know yet if it's a K counterexample. Okay, and in many ways we've like completed half of the proof. Okay, and so in the next section we're going to prove what's called the canonical model theorem, which for K, which basically is just a proof that, you know, our constructed M is a K model. And you can see that once we do that, our proof of completeness is done, right? Then we have, we'll be able to add to this, we can say that M K satisfies H and the negation of C, right? In which case we'll be able to get right that C is not a semantic consequence of H in K, in semantics K. Okay, so that's our next steps. And hopefully you've learned a little bit something from this current recording. Lindenbaum Lemma, we're going to see it again and again and again. So it's awesome, right? It's just a cool lemma, you know, and the proof of it's really cool too. But anyway, stick around, and in the next section we prove that our canonical model is a K model. Okay, hello everyone, welcome back. In this section we're going to be proving the canonical model theorem for K. And again, what this means is that we're just going to show that the canonical model that we've defined in previous sections is in fact a K model. Note that I'm going to be maybe a little less hand-holdy for some of these sections, just because I've come to the realization that this lecture is already long enough as it is, and unfortunately this is going to be the second time I'm recording this lecture. I ended up going through this entire part thinking I was recording, but then when I looked at the recording later, like for some reason my PowerPoint slide wasn't recorded, so I was just talking over a black screen, which is quite frustrating. So here's to not having to do it again. Yeah. Okay, so again, if you just need a refresher as to like why we're proving this, earlier we showed that the canonical model was such that it satisfies H and the negation of C when H doesn't prove C in K, right? So now our goal is kind of just to show that the canonical model K satisfies these sentences, right? And to do that, we show that the canonical model is a K model. And once we do that, we're done the completeness theorem. Okay. Now, recall that these are the conditions that any model must meet in order to be a K model, right? So we know they're triples of this form. And here's the first condition. W has to be non-empty. R has to be a binary relation on W. So two terms stand in the R relation at a given time, so to speak. And the elements in this relation are the elements in W. And this is the most important one. So we impose conditions on the assignment functions of K models. So basically in any K model, the way in which you assign truth values to sentences in different worlds, it's not totally like the wild, wild west, right? So you have some degree of freedom, but according to these clauses that we'll see in a second, there are just significant constraints on how the interpretations of certain sentences are given, right? And we'll see that in a moment. So this is kind of to explicate clause 3. right? So let's assume that W is an arbitrary element of W, of big W, and that we have arbitrary sentences B and C. Okay, now the first clause we'll look at is called bottom. This says that the assignment function maps bottom in every world, right? Because W is arbitrary, to false, right? So this just says that in any K model, bottom is always sent to false. And that should make sense because intuitively, bottom is supposed to represent like a contradiction, right? And contradictions are not supposed to hold. Note that you can have models in which bottom is mapped to true. Like you can do whatever you want. It's just, it won't be a K model anymore, right? But since we're only interested in K models right now, this is one condition that we have to look for. And I'll say more on the next slide about how we prove that the canonical model is a K model, right? So here's the clause for arrow, right? A maps B arrow C to true if and only if it maps B to false or C to true. This should be kind of familiar to you just based on the, well, hopefully you guys have all seen truth tables before. This is just the case. This represents just the truth table for material implication. Note that for the purposes of our proofs in what follows, we're just going to simplify it a bit. Okay, we're just going to prove these two things. And we're going to take it that once we've proved these two things, we've proved this. I'll read them both before I note that we're kind of skipping some steps, right? So arrow T says that we're kind of just breaking this down into two cases, right? So if B arrow C is mapped to true, then B is mapped to false or C is mapped to true. If B arrow C is mapped to false, then B is mapped to true and C is mapped to false. Okay, again, it's just the truth table. The reason why this is a simplification is that here we have an if and only if claim. So technically speaking, if we wanted to prove the whole thing, we'd also have to prove like this direction as well. I'm going to note in our proof of this section, like how you would do that. It's not super complicated. Just takes a few seconds. But again, this lecture is already as long as it is. And in Garson's text, he doesn't prove it either. Pull one of those moves where, if you're really curious, you can, it's left as an exercise to the reader. And it's not so bad. Again, I'll demonstrate maybe this one too, I'm not sure. Yeah, okay, so that's the clauses for arrow. Finally, we have this clause on box, right? So A maps box A to true in world W, if and only if for each world V such that W is related to V, A maps the sentence A to true in V. So that kind of corresponds to some basic stuff about box you might have seen before, right? Like box A is true if and only if in every accessible world A is true, right? That's just what this is telling you. Again, we're going to simplify this into two clauses. Again, we're not doing both directions, right? So box true says that if A maps box A to true in W, then for each V, if W is related to V, then A maps the sentence A to true in V. If A sends box A to false in W, then there exists some V such that W is related to V, and A is mapped to false in V. Okay, that's just like, when box A is false, there's some accessible world in which A is false, right? It's not necessarily true if we're thinking in terms of alethic modality. Yeah, and so what these semantic clauses do, right? There's a lot of freedom in which to assign different truth values to like different propositional variables in our language. Besides this, right? There's not much freedom with bottom, but this just tells you that for K models, once you specify the truth values of, let's say, these subcomponents, you automatically have to assign a certain truth value to like the arrow, like sentences involving the arrow, and vice versa, right? So you can't just have like, totally arbitrary. Like you can't have B mapped to true and C mapped to false and still map B arrow C to true, right? That's the clause for falsehood. So these kind of clauses take away our freedom in a certain kind of sense. And yeah, so that's just the idea, right? Because we're interested in studying models where, you know, certain logical patterns hold. And these are just the patterns that interest us with respect to K models. Okay, so the canonical model theorem for K just says that the canonical model we constructed is a K model. So recall this was our definition of our canonical model M, right? We defined W to be the set of maximal consistent sets for K. We defined our relation being as follows. W is related to V if and only if for all sentences B. If W proves box B, then V proves B. Okay. And again, this is just all stuff that we defined, right? So this is the important part, right? It's not, we have to show that like, we didn't just willy-nilly choose these things. And yeah, so we have to prove that like, based on the considerations we chose, this is a K model, okay? And we described the behavior of the assignment function in our model as follows, right? So this is like the A of our canonical model, right? So A maps the sentence A to true in world W if and only if world W proves A. Okay, so this is kind of an interesting interplay between proof and between our proof theory and our semantics. It's kind of here as well, but yeah, it's just kind of interesting the way we do it. So the way we prove the canonical model theorem, basically, I'm just going to break it into 3 sections, but all we have to do is show that each of the components of the canonical model meet the constraints for what it takes to count a model as a K model, right? So we have to show that based on our definition of W as the set of maximal consistent sets for K, we have to prove that W is non-empty, right? We have to show that our definition of R is a binary relation on W. Finally, we have to show that based on the way in which we've defined our assignment function, it obeys or is constrained by these semantic clauses, right? So if this was the A in the canonical model, then whenever B arrow C is mapped to true, the assignment function in our model also has to be forced to assign certain other truth values, right? So those are the 3 steps that we have to show. Just note that the first 2 are not too bad, but there's a certain part of this last clause that's going to be quite time consuming. And so, but we'll get there. Okay, so let's begin. I really hope this is all being recorded because yeah, it would be a bummer if not. Okay, so for this first section, note that I just have the relevant stuff from the canonical model here if you want to take a look. All right, so this first part, we have to prove that W from M is non-empty. Okay, note that here we're going to appeal to the soundness theorem for K in our proof. This was proved in chapter 8 of Garson. And if you're watching from the beginning, just note that I think in the first slide, I made a mistake in saying like where this completeness stuff takes place in the textbook. The completeness stuff is actually in chapter 9. Chapter 8 is where soundness takes place. So apologies for that. Yeah, but yeah. So what is the soundness theorem? It says that if H proves C, then, well, for K, if H proves C in K, then C is a semantic consequence of H in our semantics K. This just tells you that, you know, if you can prove something, then it's a validity, right? You can't prove things that are false in the semantics. Yeah, so if you have a proof, then it has to be true. So you rule out the case in which you have a proof of something that's like not true. Okay, so we're not going to use this form of the soundness theorem. We're actually going to use the contrapositive, right? So the contrapositive says that if C is not a semantic consequence of H in K, then H does not prove C in K. Okay. So just note the special case in which H is the empty set of sentences. right? If C is not the semantic consequence of the empty set, then there's no proof of C. Basically, this says that the theorems are true in all models. And yeah, if that doesn't make sense, it's all good. Hopefully you'll see why I bring that up in a moment. Okay, so let's prove this. Let's prove that W, the way we define W in the canonical model is such that we can show that there's at least one element in W. So we have to basically show that there's at least one maximal consistent set for K. And the proof is pretty quick, right? So recall that by definition of K models, right, bottom is mapped to F in any world W in the set of worlds of every K model, right? So, well, essentially, yeah, bottom is just always going to be mapped to false, okay? So every world in every model is such that the assignment function A maps bottom to false. Note that by definition, K models, their set of worlds is non-empty. So there's going to be at least one counter example, let's say, to bottom, right? There's always going to be at least one W such that A in W maps bottom to false, right? This is just, by definition, K models have to have at least one world in which this occurs based on, the definition of the set of worlds in K models and the assignment function in K models. Okay, so since we have this, right, by the soundness theorem, we have that there's no proof of bottom in K, right? Alternatively, this means that the empty set of sentences does not prove bottom, right? But note that the empty set is a set and that this is simply our definition of consistency in K, right? So sentence S is consistent in K if on the basis of K, you can't prove a contradiction from S. And this is exactly what we have here. So therefore, the empty set is consistent in K. But notice it's a set and it's consistent. So by Lindenbaum Lemma, there exists an MC set W. That's an extension of the empty set. So every element of the empty set is an element of W. That's just trivially going to be the case. If you know a little bit about set theory, it's like how the empty set is a subset of every set, just like vacuously. Of course, this MC set W has the additional property of being consistent and maximal. Right? Now, by definition of W in the canonical model, W is just going to be an element of big W, right? It's an MC set that's an extension of a set that's consistent in K. W is consistent in K. Therefore, we know that big W from our canonical model is non-empty. There's at least one element in there. Cool. Constraint 1 is finished. Let's move on. Okay, so part 2. I'm just going to be a bit wishy-washy with this. Okay, so recall this is our definition of R. And this is what we need to show, that R is binary, meaning that only 2 elements stand in R at any given time. Again, I don't want to go too deep into the semantics of relations, but hopefully it's like clear enough. We'll see that there's enough work with the assignment function section, regardless. So this was our definition, right? W is related to V if and only if for all sentences B. If W proves box B in K, then V proves B. Okay. As we can see, the elements of R are the elements of W, right? Because W and V and like lowercase w and V are supposed to be elements of W. And R is binary, right? There's only 2 things that are related to each other at a given time. So R from our canonical model is a binary relation. Again, that's just very quick. It's pretty quick in Garson as well. Okay, let's move on to constraints for the assignment function in M. Okay, note that this is just the section that takes the longest amount of time. Okay, now recall this is our definition of A from the canonical model, right? A sends an arbitrary sentence to true in a world W if that world W proves A. Okay. Notice that W is MC. Okay. So these are the semantic clauses, again, that we have to check. I should note that it's equivalent star to the conjunction of arrow true and arrow false. That's a notation thing. For our purposes, they're equivalent. Again, I'll just note real quick how we prove the other direction as well. But yeah. All right, so let's start checking each of these things. Okay, again, this is our assignment function from the canonical model. So in our first section, we want to show that based on this A that we've defined, this comes out as always happens, basically, right? So we have to show that on our definition of A maps bottom to false in every world. Now note this important trick, right? In order to show this, it suffices to show this. Why? Because these are actually equivalent based on the definition of A, right? So this says A maps a certain sentence to true in a world W if and only if that world proves A. Okay, it goes the other way too, right? If W proves A, then we know that our assignment function has to send A to true. Okay, so we're just gonna see that it's easier working with worlds, right? So we have to just prove this. Okay, so here's the proof that W does not prove bottom. Straightforward. W is an arbitrary element of big W. So we know that all the elements of W are MC in K. Right? So by definition of consistency, W does not prove bottom in K. Therefore, again, by this translation thing, we have that A maps bottom to false in W, in arbitrary world W. So there you go. We know that our assignment function behaves according to this semantic clause for every K model. Cool. Let's move on. Here are the clauses for arrow, right? So recall we're just going to prove these two. So let's prove that our assignment function obeys arrow true. Again, by that translation scheme, this amounts to proving that if W proves B arrow C, then then W does not prove B or W proves C. Again, if you just take this and replace it, right, with the clause for W based on our definition, you'll see that it all maps accordingly, right? Now I have a note here. Okay, so let's prove this. Okay, so we're going to assume that W proves B arrow C. Next, we appeal to a tautology, law of an instance of the law of exclude mill, right? So either B or the negation of B is in W. Well, actually, I guess we're not really appealing to law of exclude mill. Kind of also follows from the fact that W is MC. So maybe disregard that. So let's break this into cases. Right? So case one, B is in W. What does that mean? If B is in W, then we have a one-step proof of B from W, right, by the reiteration rule. Okay, since we know that W proves B and W proves B arrow C, we know that W proves C, right, by modus ponens. Okay, so if we assume one of these, then we get one of the disjuncts that we're looking for. Okay, opposite case, the negation of B is in W. So again, we're going to have a one-step proof in which W proves the negation of B. Okay, and note that we want to show that in this case, we'll have that W does not prove B. So let's assume that W proves B for contradiction proof. Okay, but if we assume these two things, then that means W proves the negation of B and W proves B, which means that W proves bottom. right, by indirect proof. But we know that this is a contradiction because W is MC. Namely, it's consistent. So there's a contradiction. Therefore, does not prove B. Okay, there you go. On the basis of assuming that W proves B arrow C, we either have W proving C or W not proving B. And that's exactly what this clause tells us. So we have proved that A obeys arrow T. Real quick, if you're interested in like the other direction, you would just assume as follows, right? So step one, assume that W does not prove B or W proves C. Okay. And okay, so begin by assuming one of them, right? And then assume the opposite of what you're trying to show. So assume that W does not prove B arrow C. Okay. But then we know that B arrow C is not going to be an element of W, right? Because if it were, then W could prove it. But since W is MC, we're going to have that W proves the negation of B arrow C, right? Because since it's maximal and this is not an element of W, we know that the negation of B arrow C is in W. So therefore, W proves the negation of B arrow C. But then by arrow false, we have that W proves B and W proves the negation of C. Here's our contradiction, right? We assume that W does not prove B, and here we've proven that W does prove B. So this was our false assumption. So therefore, W proves B arrow C. Okay, similarly for this case, we assume the same thing, right? So now we're going to have, and like all of this is just going to be the same, right? So now we have W proves C. We get this step, that W proves the negation of C, which means that W proves bottom, which again is a contradiction because, like we saw here, W is MC. And so again, we're going to have that W proves B arrow C. Okay, so it's straightforward stuff like that. We're going to omit, like I said, the other direction. Okay, cool. So that's one. That's arrow T. Now we have to do arrow F. Okay, this says that if A maps B arrow C to false, then A maps B to true and A maps C to false. So similarly, we're going to do this translation thing again based on the definition of the assignment function. So what we're going to prove is if W does not prove B arrow C, then W proves B and W does not prove C. Okay. So let's assume that W does not prove B arrow C. It follows that B arrow C is not in W, right? Again, because if it were, then W would be able to prove it, which would mean that W proves B arrow C and W does not prove B arrow C. Okay. Yeah. Now, since W is maximal consistent and B arrow C is not in W, we know that the negation of B arrow C is in W. And so again, by one-step proof of REIT, we're gonna have that W proves the negation of B arrow C. Okay, so we have this. Now we want to show that W proves B and W does not prove C. Note that our derived rule of inference that we appealed to in the last slide, arrow F, tells us that since W proves the negation of B arrow C, W proves B, and W proves the negation of C. Okay, then it's very easy to see that W does not prove C, right? Because if we assume that W proves C, then W would be able to prove bottom because it would then prove the negation of C and C, which is impossible because it's consistent. So W can't prove C. Okay, so on the assumption that W does not prove B arrow C, it follows that W proves B and that W does not prove C. Again, by this translation schema that we have, we've shown that if A maps B arrow C to false, then A maps B to true and A maps C to false. Okay, so our assignment function also is constrained in the appropriate way by arrow falsehood. Okay, let's continue. So we're moving on to the box case. I'm just going to flag box F is I'm going to do a separate slideshow or presentation on that just because it's so complicated. We're going to need like 4 different lemmas to prove it. I'll explain why in a moment. But let's first just deal with box T. This says that if A sends box A to true in W, right, here the worlds matter, then for each V in W, if W is related to V, then A maps the sentence A to true in V. Again, we're going to be proving that if W proves box A, then for each V in W, if W is related to V, then V proves A. Okay, so assume that W proves box A, and let V be any member of W such that W is related to V. Note again that we're working within the canonical model, right? We want to show that our model is a K model, right? So this R is this R, okay? Now by the definition of R, right, it says that for all sentences B, if W proves box B, then V proves B. Since we're assuming that V is a member of W and W is related to V, and since we have this, and since we have that W proves box A, because W is related to V, we have that V proves A as desired, right? So there you go. Therefore, if W proves box A, then for each V in W, because V, V is arbitrary. If W is related to V, then V proves A. Okay. Now, by the definition of A, we have shown that if A maps box A to true in W, then for each V, if W is related to V, then A maps A to true in V. And that's exactly what box T is telling us. So A obeys box T. Hooray. Okay, so I'm going to pause here, but I'm going to briefly note why I'm pausing here. Okay, so here again is the last clause that we need to check before we're done. Okay, hooray. But life just makes things difficult for us sometimes. Right, so this says, if A sends box A to false in W, then there exists some V such that W is related to V, and A maps the sentence A to false in V. Okay, so in many ways, this is going to be the hardest part of proving completeness. At least for the definition, or for the canonical model theorem for K. That Lindenbaum Lemma stuff is pretty nuts too. But this is like the other hard part. Okay, so why is it so difficult? So note that we're going to appeal to that translation thing before. So we're going to take box F and put it in this other form, box F star. So what we need to show is that if W does not prove box A, then there's some V such that W is related to V, and V does not prove A. Okay. Now, the issue is going to be in selecting the appropriate V such that V does not prove A. So we're going to see that we need a number of lemmas in order to construct the right kind of world in which this happens, right? So yeah, stick around. That's going to be the subject of our next lecture, and hopefully you enjoyed this part. All right, see you soon. All right, hello everyone, welcome back. This is the final part of the main lecture. And I noted last time that we paused right before proving this last section of the canonical model theorem for K. which was that the assignment function in K obeys this semantic clause that is a feature of all K models. Remember, this amounted to proving that if W, an arbitrary element of big W in our canonical model, right? If W does not prove box A, then for some V such that W is related to V, V does not prove A. Okay. And yeah, let's go on and prove it. Okay. Okay, so the first lemma that we're going to use is quite straightforward. It's called the extension lemma. Okay, this says if M prime is an extension of M, then if M proves A for an arbitrary A, or any A, then M prime also proves A. Okay, so here's the proof. We assume the antecedent, we assume that M proves A. Okay, since M proves A, we know that there's some list of members of M, H, such that H proves A, right? This is because proofs are finite. I mentioned this in an earlier note. Okay, but since M prime is an extension of M, right? Every element of M, M is an element of M prime. And we know that the H's all, or the H all comes from M, so therefore H is in M prime. So we know that H is in M prime, but since H proves A, it's going to continue proving A, so M prime proves A. So that's the extension lemma. Again, pretty straightforward. We don't even need like a subscript or anything. This just follows naturally from the definition of proofs as finite. Okay, now before we state the next lemma, we first have to give some definitions. Okay, so first, just consider an arbitrary W of big W in our canonical model, right? We know that W is just going to be MC by construction of W. So we know that many of the sentences of W will be prefaced with a box, right? Because for any sentence A of our language, either A or not A is in W, right? But we know that like box, whatever are sentences. So some of these are going to be boxes, right? So we know that whenever S is a sentence, box S is a sentence. So some of the stuff in W is going to be prefaced with box. Okay. Now we're going to define a set V as follows, right? Now consider an arbitrary sentence B of our language, and we're just going to use this symbolism to mean is a member of, okay? So we define V as follows. An arbitrary sentence is an element of V if and only if its boxed version is an element of W. Okay, so here's an example just to illustrate the process. Note that this is just a toy example, right? The W's that we're interested in are maximal. They're gonna have a lot of things in them, but here we just have some whatever random sentences, right? So based on this definition, okay, well, notice that this is a box sentence. So box A is an element of W, so we know that A is going to be an element of V. Okay. Box A and B is an element of W, so we know that A and B is an element of V. This is not a boxed formula or sentence, doesn't matter. Neither is this, but this is, okay, so we have that A arrow C, okay, is a sentence of V. And this again all follows based on how we've defined our set V. Okay. Next, we're going to define the set box V as follows. So box V is obtained from V by taking every sentence in V and adding a box in front of it. So continuing with the last example, right? We just look at V. None of these are going to have boxes, right? Well, they could, but doesn't matter. Yeah. It could if in W we had like box A, right? But anyway, that's doesn't matter. Okay. So in our example we were working with before, box V is going to look like this, right? It contains box A, right? Because A is an element of V and we're adding box to it. We're going to have box A and B. Okay. We're going to have box A arrow C. So the idea is that if an arbitrary sentence S is an element of V, then box S is an element of box V. That's just how we've defined box V. Note, box V is not just W, even though it looks similar to W, right? For example, B is an element of W, but B is not an element of box V. However, right, maybe you're noting that there is some connection between W and box V, and that's one of those connections is going to be stated in our next lemma. Okay, so this is called the V lemma. This just says that W, right, an arbitrary MC set of our canonical model is an extension of box V. Okay. Now, by definition of extension, right, we have to prove that every element of box V is an element of W. Okay. So here's how we're going to prove it. Let's let C be an element of box V, right? Now recall by the definition of box V, C is going to be of the form box S for some sentence S in V. This is just by this definition. Now by definition of V, right, this definition, since S is an element of V, we have that box S is an element of W. Okay, that's just how we've defined V in box V. But since box S was just C, and C was an arbitrary element of box V, we've proved that every element of box V is an element of W, right? We've proven it for an arbitrary element of box V. So that's just what it means for W to be an extension of box V. Right, we've proved the V lemma, yay. Okay, onwards, there's just two more lemmas that we need. Okay, the next lemma is called the consistency lemma. This says that if W does not prove box A, then the set containing V and the negation of A is a consistent set in K. Okay, recall that this is just the result of adding the negation of A to V, right? So we're going to assume that W does not prove box A. We're going to use a contradiction proof and assume that V comma not A is not consistent. Okay, by definition, that means that V and the negation of A prove bottom. Okay. Now, since proofs are finite, there exists some set H and the negation of A of elements of V with the negation of A, such that H with the negation of A proves bottom. Okay, it's just because proofs are finite. Now, by indirect proof, we have that H proves A. Here's the only time where we use general necessitation, right? Recall that it says that if D proves E, then box D proves box E for any sentences D and E. If you want to recap, you can go back to very early on in this lecture. I went over this. Now, since we have that H proves A, by general necessitation, we have that box H proves box A. As a notational thing, right? Box H is just going to be the result of prefacing each element of H with box. Okay. Now, since each element of H is an element of V, right? Because we obtained it up here from the fact that V and the negation of A proves bottom, we know that V is an extension of H, right? In other words, we'll write that H is an element of V. Now, by definition of box V, right? If an arbitrary S is an element of V, then box S is an element of box V. We have that box H is an element of box V, right? Because H is an element of V. So this just tells us that every element of box H is an element of box V. Okay. By definition of box H, right? And definition of box V. Now, by the V lemma, we have that W is an extension of box V. Therefore, we can conclude that W is an extension of box H. If you want a quick proof, let's let X be an arbitrary element of box H. Since we have that box V is an extension of box H, we have that X is an element of box V. Since W is an extension of box V, we have that X is an element of W. Okay. And there you go. This is an arbitrary element of box H. So every element of box H is an element of W, which is just what it means for W to be an extension of box H. Okay. And yeah, note here, this is where we have it explicitly noted that box V is an extension of box H. Okay. Now, by the extension lemma, right, since box H proves box A and W is an extension of box H, we have that W proves box A. Okay. But this violates our initial assumption up here, right, because we assumed that W does not prove box A. And now we've just shown that W proves box A. That's a contradiction. This was for our contradiction proof, right, up here. So the assumption that V and the negation of A was not consistent led us to a contradiction. And so we conclude that V with the negation of A is consistent. And there you go. We've proved the consistency lemma. If we assume that W does not prove box A, it follows that V and the negation of A is consistent in K. All right, one last lemma, and then we're done. Okay, so this last lemma is called the R lemma. Okay, it says if V is an extension of the set of sentences V and the negation of A, then W, arbitrary W, is related to V. Okay, so assume that V is an extension of V and not A. Now recall the definition of R in the canonical model, right? Assume that S is an element of big W, right? So W is related to S if and only if for all sentences G. If W proves box G, then S proves G, right? So it follows that from one half of the definition, in order to prove that W is related to S, we have to prove that if W proves box G, then S proves G. So in order to prove that W is related to V, we have to prove that if W proves box G, then V proves G. Okay, so here's our proof. We assume that W proves box G. We know then that box G is an element of W. Again, because if the negation of box G was in W, well, let me step back a bit. If box G was not in W, then by maximality, we have that the negation of box G is in W, which means that W proves the negation of box G, which would mean that W is inconsistent, which violates the assumption that it's an MC set, right? So we have to have that box G is an element of W, right? By the definition of V, our set V, it follows that G is an element of V, right? Because box G is an element of W, therefore G is an element of V. But clearly, the set containing V and the negation of A is an extension of V. And since G is an element of V, G is also going to be an element of V, comma, the negation of A. And since we started off up here by assuming that V is an extension of the set V and the negation of A, we're also going to have that G is an element of V, right? Because G is an element of V with the negation of A, and V is an extension of that set, which means every element in here is an element in here, right? So G is an element of V. Therefore, V proves G, again, by re-it, it's just a one-step proof. Therefore, we've proven that if W proves box G, then V proves G. right? But that's just what it takes to prove that W is related to V. And so we've proven that on the assumption that V is an extension of V comma not A, it follows that W is related to V. And that's just what the R lemma says. Okay, let's just do a quick pause and go over what we've done. So recall we defined a set V as follows. Sentence S is an element of V if and only if box S is an element of W, where W is just an arbitrary element of W from our canonical model. Just make that clear. Box V was obtained by prefacing each sentence S of V with a box. Okay, the extension lemma says that if M prime is an extension of M, then if M proves something, then M prime continues to prove that same thing. Our V lemma told us that W is an extension of box V. Our consistency lemma told us that if W does not prove box A, then the set V and the negation of A is consistent. And our R lemma tells us that if V is an extension of V in the negation of A, then W is related to V. Okay. Let's finally remind ourselves of what we wanted to prove, namely that the assignment function of our canonical model obeys this clause, which says that if W does not prove box A, then for some V such that W is related to V, V does not prove A. Okay, so let's prove this. All right, so we're gonna start by assuming the antecedent. Okay, W does not prove box A. This is the consistency lemma. So by the consistency lemma, we have that V with the negation of A is consistent, right? But this is just a set of sentences. So we have a consistent set of sentences. By Lindenbaum Lemma, we extend this set of sentences to an MC set V, right? So V is an extension of the set V with the negation of A and is maximal consistent. So we know that V is an element of W in our canonical model. Now by the R lemma, right, if V is an extension of V with the negation of A, then W is related to V. We know that, so we know that W is related to V, right, because of the antecedent right here. Now, since V is an extension of the set V with the negation of A, right, so every element in here is an element in here, clearly the negation of A is going to be an element of V. And so clearly V is going to be able to prove the negation of A, again, by re-it, one step. Okay. Now, assume, right? Assume for contradiction proof that V proves A, right? Again, recall that we're trying to prove that V does not prove A. So if so, we have that V proves bottom, right? Because then V proves A and V proves the negation of A, sorry, and V proves A. Okay, in which case by bottom in, we have that V proves bottom, which is a contradiction because V is consistent. So therefore V cannot prove A. So now we're done, right? Under the assumption that W does not prove box A, we found a V that's an element of W from our canonical model, such that W is related to V and V does not prove A. Now recall that by using the definition of A, we obtained box F star, right? We've really, by proving box F star, we've proven box F, right? If our assignment function from the canonical model maps box A to false in world W, then there exists some V such that W is related to V, and the assignment function maps the sentence A to false in V. Okay. Now, since A obeys both box T and box F, we have that our assignment function obeys the semantic clauses for box, and therefore the assignment function A of our canonical model satisfies condition 3 on K models. All right, we're basically done, right? We've just proved that the canonical model is a K model. Again, here's our definition of our canonical model M, right? This was our set W. This is how we defined the relation. This is how we defined our assignment function, right? We've shown that W from our canonical model is non-empty. We've shown that the R we defined is a binary relation on W. And finally, we've shown that our assignment function in the canonical model obeys the semantic clauses on K models. So since we've shown that M meets each of these constraints, we have that M is a K model. All right. So just quickly zooming out, we wanted to prove the contrapositive of the completeness theorem, which says that if H does not prove C in K, then C is not a semantic consequence of H in K or in K models, right? Basically according to our semantics, right? And that amounted to showing that if H does not prove C, then our canonical model was such that H and the negation of C was satisfiable. After proving that the canonical model is in fact a K model, we have that the canonical model K satisfies H and the negation of C. So we've shown that C is not a semantic consequence of H under the assumption that H does not prove C. So we've proven the completeness theorem for K. Hooray. And yeah, so hopefully you enjoyed that. That's basically the end of the official lecture. If you're interested, stick around for a few more minutes. I'm just going to quickly go over some bonus material that kind of lends some justification or interest for this particular way in which we prove the completeness theorem. There are other ways to prove this theorem. The specific way we did it was using like this canonical model stuff. And the bonus material is just gonna say why the canonical model construction is such a powerful proof method. And just to give you a sneak peek, it's powerful because this method of proof is essentially the same for any proof system based on K, right? So if you've heard of stuff like S4, S5, B, D, all those modal logic systems, basically the canonical model construction will give us proofs or give us completeness theorem proofs for those systems in a very easy way. And so, yeah, but if you're not interested, that's totally fine. You've suffered and you've made it through the official lecture. And I just want to say thanks for listening. All right. All right, final part. All right, everyone. Thanks to those who stuck around for the bonus material. Gonna show you what we can kind of do now that we've seen this proof method. Okay. So recall that our system K was just the result of adding, additional rules to the system of propositional logic, right? Now, we're also sometimes can be interested in various other systems based on K. And what this means is that we those systems based on K are just like K, except we add additional rules of inference or axioms. So for example, consider the M axiom that says box A, arrow A, right? So whenever you have box A, you can infer A, let's say. And then we can define a new system M as K plus this M axiom, right? So you can do similar stuff, right? System D is the result of adding the D axiom to K. Okay, it says box A, arrow, diamond A. B, for instance, says A, arrow, box, diamond A. You have 4, box A, arrow, box A, and S5. And each of these ones are like based on K in that if you add these sentences to the appropriate system or system based on K, you get like a new logic. Okay. So these are like some of the other systems that we might be interested in. Now, the canonical model construction allows for like some much more streamlined proofs for these systems. For example, let's look at the completeness theorem for M. Okay, it looks just like K, except that we switch out the K subscripts for M subscripts, right? So it says that if H does not prove C in M, then C is not a semantic consequence of H in M models. So there's at least one world in one M model such that H and the negation of C is satisfied. And recall that we proved completeness in 2 stages, right? The first was to show that the canonical model we construct is such that it satisfies H and the negation of C. And in stage 2, we showed that the canonical model is a K model, right? So this is completeness for K. So the idea is that completeness proofs for systems like M, for instance, are also going to break down into these 2 stages. Okay. Interestingly, stage 1 of our completeness proof, right? This part, it basically looks the exact same for like the M case, right? If you go back to that part of the lecture, we see that that proof was like at like a very general proof, didn't appeal to any of the particular features of K. And so although you have to change some slight details related to like, you know, subscripts or whatever, we've basically done most of the work for stage 1. So it's like almost, we're already like halfway there, right? So what's the second part, right? So naturally, the focus is going to be on showing stage 2, right? That when the canonical model satisfies H and the negation of C, under the assumption that H does not prove C in M, we just have to prove that the canonical model M satisfies H and the negation of C, i.e. that the canonical model is an M model, right? So again, the question is, how do we show that it's an M model? Here's just a quick recap, okay? Remember that the tuple W and R consisting of the WR from like a model is called, of a model M, is called M's frame, right? Now, one property of systems based on K is that the frames of their models are just K frames plus some additional constraints. So we saw this before, right? In class, M models are just like K models, except that M frames are reflexive, whereas K models don't have to be, right? So this frame WR is reflexive if and only if W is related to W itself for all the W's in big W, right? So to prove that the canonical model is an M model, we show that R of the canonical model, right, is reflexive when axiom M is added to K. We do this because every M model will prove the axioms of M, right, including the M axiom. So once we've proven this, the completeness theorem for M is done, right? So based on this canonical model construction, like the only thing left to do really is to prove that the canonical model is an M model via showing that its frame is reflexive. I guess technically this should be that its frame is reflexive, right? Similarly, right, we saw that by adding this axiom to K, we obtain system D. Here, D frames are just like K frames, except that D frames are serial, right? So a frame is serial if and only if for all W in W, there's some V in W such that W is related to V, right? So every world is related to some other world, or every world is related to some world, right? Now, to prove completeness for D, we just have to prove that the canonical model is a D model, which means proving that the frame of the canonical model is serial, right? That is, has this property, this property, when this axiom is provable, okay? Similarly for all the other systems I mentioned earlier, right? Because the models or the frames in the model of like B models, for instance, S4 models, S5 models, are all just they all correspond with additional features on K frames, right? So S4 frames are transitive and reflexive, B frames are symmetric, S5 frames are equivalent, i.e. they're equivalence relations, i.e. they're symmetric, transitive, and reflexive, right? So for example, to prove that, I guess this should technically be the frame, right? So to prove that the frame of the canonical model is symmetric when B is provable is to prove the completeness theorem for B. Similarly, right, proving that, typos, sorry. Proving that this frame is reflexive and transitive when 4 is provable amounts to showing that S4 is complete, and so on. And so that's just one cool feature of the canonical model construction as a method for proving the completeness theorem for K, right? It makes the completeness theorems for these other systems a lot more straightforward, or at least streamlined in a certain sense, right? And so, yeah, that's just a cool little feature of this method of proof. And yeah, if you're interested in the details, you can see chapter 9 of Garson's text. Yeah, I've decided to omit a lot of those details, but yeah, that concludes this lecture in its entirety. And I just want to say thanks to everyone who listened to this. Hopefully you learned something. And I hope you have a lovely day. All right, thanks for listening. See ya.